Venus, a celestial body often referred to as Earth's twin due to its comparable size and composition, presents a stark contrast to our home planet. Its environment, veiled in mystery and characterized by extreme heat and density, poses a fascinating puzzle for scientists and curious minds alike. Our exploration begins with a simple yet powerful analogy: the pressure cooker. Imagine this common kitchen appliance tightly sealed, with water simmering inside. As the heat intensifies, the water transforms into steam, and the pressure within the cooker escalates dramatically. The steam, confined within this limited space, cannot escape, leading to a significant increase in density. This scenario mirrors the fundamental condition of Venus's atmosphere, albeit on an immensely larger and more intense scale. Venus's atmosphere is incredibly dense, approximately 90 times denser than Earth's. To put it into perspective, it's akin to being submerged at the bottom of a deep ocean trench on Earth, crushed under the immense weight of the water column above. Let's transition to another illustrative analogy: the greenhouse. This structure, designed to cultivate plants, utilizes glass panels to allow sunlight to penetrate, warming the interior. However, the glass effectively traps the heat, preventing it from easily escaping, thus creating a warmer environment inside compared to the outside. This phenomenon is known as the greenhouse effect, a natural process that plays a vital role in sustaining life on Earth. It acts as a thermal regulator, trapping a portion of the sun's energy to maintain a comfortably warm temperature. However, on Venus, this crucial effect has gone awry, transforming into a runaway process with devastating consequences. The primary constituent of Venus's atmosphere is carbon dioxide, a well-known and potent greenhouse gas. Visualize carbon dioxide as the glass panels of our greenhouse, but multiplied exponentially in thickness and effectiveness. On Earth, carbon dioxide constitutes a mere fraction of our atmosphere, around 0.04%. In contrast, on Venus it comprises a staggering 96%. This thick, impenetrable blanket of carbon dioxide traps an enormous amount of solar radiation, far exceeding the amount it allows to escape back into space. This imbalance leads to the infamous runaway greenhouse effect, the primary driver of Venus's extreme temperatures. To grasp the sheer magnitude of this effect, let's consider a scenario familiar to many: a car parked under the blazing summer sun with its windows rolled up. As the day progresses, the car's interior becomes unbearably hot, transforming into a miniature furnace. The car's interior acts as a microcosm of Venus, with the windows trapping the incoming solar radiation and preventing the heat from escaping. Now imagine that car's interior is filled with a dense, opaque gas that is even more efficient at trapping heat than air. That's the stark reality on Venus. The consequence of this runaway greenhouse effect is a surface temperature that averages a scorching 464 degrees Celsius, 867 degrees Fahrenheit, hot enough to melt lead, making Venus the hottest planet in our solar system. However, the story of Venus's atmosphere is far more intricate than just density and the greenhouse effect. It involves a complex interplay of various factors, each contributing its unique share to the planet's extreme nature. Let's explore another analogy, one that highlights the slow yet relentless power of erosion. Imagine a river, steadily carving its path through a landscape over millions of years. The water, seemingly gentle in its flow, gradually wears away the solid rock, sculpting valleys and canyons over vast stretches of time. This process, though operating at a snail's pace, exerts a profound influence on the landscape over geological timescales. Similarly, on Venus, the intense heat and pressure have, over eons, dramatically altered the planet's surface and atmosphere. The extreme conditions have likely triggered a process called outgassing, where gases trapped deep within the planet's interior are gradually released into the atmosphere. This process is analogous to the river eroding rock, but instead of rock, it's the planet's internal composition that undergoes transformation and release. This outgassing has significantly contributed to the buildup of carbon dioxide in Venus's atmosphere, further fueling the runaway greenhouse effect, creating a positive feedback loop that intensifies the heating. Now let's shift our focus to another crucial aspect: the absence of a significant magnetic field. On Earth, our planet's robust magnetic field acts as a protective shield, deflecting the harmful solar wind, a continuous stream of charged particles emanating from the sun. Think of it as a sturdy umbrella, effectively shielding us from a downpour of raindrops. Venus, however, lacks a strong magnetic field, leaving it vulnerable to the full force of the solar wind. As a result, the solar wind directly interacts with Venus's upper atmosphere, creating a dynamic and complex interplay. This interaction can be likened to a relentless sandblaster, gradually stripping away lighter elements like hydrogen and helium from the upper atmosphere. Imagine a strong wind persistently eroding a sand dune, carrying away the lighter particles while leaving behind the heavier ones. Over billions of years, this process, known as atmospheric escape, has likely contributed to the significant loss of water from Venus. Water molecules, when broken down by intense solar radiation into their constituent hydrogen and oxygen atoms, are more easily stripped away by the solar wind in the absence of a protective magnetic shield. The loss of water has profound implications for Venus's atmosphere and its evolution. Water vapor is a potent greenhouse gas, even more effective than carbon dioxide at trapping heat. The gradual disappearance of water might have played a crucial role in exacerbating the runaway greenhouse effect on Venus. It's analogous to removing a key ingredient from a complex recipe. The final dish turns out drastically different. In Venus's case, the loss of water has contributed to its transformation into an incredibly hot and arid world, a stark contrast to the potentially habitable environment it might have had in its early history. Let's introduce another earthly example to further illuminate Venus's atmospheric story, the slow yet powerful process of plate tectonics. On Earth, the planet's crust is fragmented into large plates that are in constant, albeit slow, motion. These plates interact with each other, shaping continents, creating majestic mountain ranges, and triggering earthquakes and volcanic eruptions. This dynamic process also plays a crucial role in regulating Earth's climate over long timescales. Plate tectonics facilitates the carbon cycle, a complex global process that involves the exchange of carbon between the atmosphere, oceans, and Earth's interior. Imagine it as a sophisticated, planet-wide recycling system for carbon. When volcanoes erupt, they release carbon dioxide into the atmosphere, adding to the greenhouse effect. This carbon dioxide dissolves in rainwater, forming a weak acid that weathers rocks exposed on the Earth's surface. The weathered materials carrying carbon within them are eventually transported to the oceans by rivers and streams. In the oceans, this dissolved carbon is incorporated into the shells and skeletons of marine organisms. When these organisms die, their carbon-containing remains sink to the ocean floor, accumulating over time, and eventually forming carbonate rocks like limestone. Over millions of years, these carbonate rocks are subducted back into Earth's interior through the process of plate tectonics, effectively sequestering carbon deep within the planet. This completes the long-term carbon cycle. This intricate carbon cycle acts as a natural thermostat, helping to stabilize Earth's climate over geological time periods. If atmospheric carbon dioxide levels rise, increased weathering rates remove more carbon from the atmosphere, reducing the greenhouse effect and counteracting the warming trend. Conversely, if carbon dioxide levels fall, weathering slows down, allowing carbon dioxide to accumulate in the atmosphere, enhancing the greenhouse effect, and counteracting the cooling trend. It's a self-regulating system that helps maintain a relatively stable climate. Venus, however, appears to lack active plate tectonics as we observe on Earth. Its surface seems to be a single, continuous plate without the dynamic movement and recycling of crustal material. This absence has significant implications for its atmosphere and long-term climate evolution. Without plate tectonics, there is no efficient mechanism to recycle carbon back into the planet's interior. Carbon dioxide released through volcanic outgassing accumulates in the atmosphere, unchecked, further intensifying the greenhouse effect. It's like a recycling plant shutting down. The waste materials pile up with nowhere to go, creating an ever-growing problem. The lack of plate tectonics might also be connected to another peculiar feature of Venus's atmosphere, its superrotation. The upper atmosphere of Venus rotates astonishingly faster than the planet itself, circling it in just 4 Earth days, while the planet takes a sluggish 243 Earth days to complete one rotation on its axis. This phenomenon can be visualized as a giant atmospheric hurricane constantly encircling the planet at high speeds. The exact cause of this superrotation is still a subject of scientific debate, but one prominent hypothesis involves the absence of significant topographical features on Venus's surface. On Earth, mountain ranges, valleys, and other surface variations create friction that slows down atmospheric circulation, preventing it from reaching extreme speeds. Venus, however, has a relatively smooth surface, lacking the large continent-scale mountain ranges found on Earth. This lack of significant surface friction might allow the atmosphere to spin more freely and rapidly, leading to the observed superrotation. It's like a spinning top encountering less resistance on a smooth surface, allowing it to spin faster and for a longer duration. Another contributing factor to the complex mysteries of Venus's atmosphere is the presence of thick, globe-encompassing clouds composed primarily of sulfuric acid. These clouds, unlike the water-based clouds familiar to us on Earth, are highly reflective, acting like a giant mirror in the sky. They reflect a significant portion of the incoming sunlight back into space, preventing it from reaching the surface. One might initially think that this reflectivity would cool the planet, but, paradoxically, it contributes to the intense surface heat. These reflective clouds, while bouncing sunlight away, also act as an effective blanket, trapping the heat that radiates from the planet's scorching surface. It's analogous to wearing a reflective jacket on a hot day. The jacket reflects sunlight, providing some protection from the direct solar radiation, but it also traps your body heat, making you feel even hotter. The sulfuric acid clouds on Venus create a similar effect, contributing to the extreme surface temperatures by preventing heat from escaping into space. The formation of these sulfuric acid clouds is another fascinating aspect of Venus's atmosphere, involving a complex interplay of chemical reactions. The process likely involves chemical reactions between sulfur dioxide, water vapor, in the trace amounts that remain, and oxygen in the atmosphere. These reactions are driven by the intense solar radiation and the high temperatures and pressures prevalent in the Venusian atmosphere. It's like a complex chemical experiment taking place on a planetary scale, with the atmosphere acting as a giant dynamic reaction vessel. The presence of these thick, opaque clouds also poses a significant challenge for studying Venus's surface from orbit. The dense cloud cover obscures the surface from view, making it challenging to use conventional imaging techniques to study its features. Scientists have had to rely on radar mapping, a technique that uses radio waves to penetrate the clouds and reveal the hidden landscape below. It's like trying to see through a dense fog. You need special tools and techniques to pierce the veil and understand what lies beneath the obscuring layer. The study of Venus's atmosphere is not merely an academic exercise confined to the realm of planetary science. It holds important lessons and implications for understanding our own planet and the potential consequences of altering the composition of our atmosphere. Venus serves as a stark cautionary tale, a vivid reminder of what can happen when the greenhouse effect runs unchecked, spiraling out of control. It highlights the delicate balance of factors that maintains Earth's habitability and the crucial importance of preserving that balance for future generations. By studying Venus, we can gain valuable insights into the long-term effects of increasing greenhouse gas concentrations in our own atmosphere. The runaway greenhouse effect on Venus serves as a potential, albeit extreme, end-member scenario for what could happen on Earth if we continue to release large amounts of carbon dioxide and other greenhouse gases into the atmosphere through human activities. It's like looking into a distorted mirror that reflects a possible future, a future we must strive to avoid through responsible stewardship of our planet. Furthermore, the study of Venus can shed light on the evolution of planets in general, providing valuable clues about the diversity of planetary environments in our solar system and beyond. By comparing and contrasting the atmospheric evolution of Earth and Venus, two planets that started with similar compositions but diverged dramatically in their evolutionary paths, we can gain a better understanding of the factors that determine a planet's habitability. It helps us answer fundamental questions about the conditions necessary for life to arise and thrive, and the likelihood of finding habitable worlds beyond our solar system in the vast expanse of the universe. The mysteries of Venus's atmosphere are complex and multifaceted. The dense, carbon dioxide-rich atmosphere, the runaway greenhouse effect, the absence of a magnetic field and plate tectonics, the super-rotating atmosphere, and the reflective sulfuric acid clouds all contribute to creating a world vastly different from our own. A world that has followed a dramatically different evolutionary trajectory. These unique atmospheric conditions make Venus both a scientific puzzle and a key target for future exploration, as understanding its past may offer insights into Earth's own climate evolution. The story of Venus's atmosphere is a story of a planet that took a different evolutionary path than Earth, a path that led to extreme conditions. It's a story of a world where the delicate balance that maintains habitability was disrupted, leading to a scorching, inhospitable environment. It's a story that serves as a valuable lesson for humanity, a reminder of the importance of understanding and protecting our own planet's atmosphere, the thin, fragile layer that sustains life as we know it. As we continue to explore Venus using sophisticated spacecraft and advanced remote sensing techniques, we gain not only knowledge about a neighboring world, but also a deeper appreciation for the unique and precious nature of our own blue planet, a haven for life in the vastness of space. The journey to understand Venus is ultimately a journey to understand ourselves, our place in the universe, and the profound responsibility we have to safeguard the future of our home planet.